I understand very well that I'm now standing between you and lunch, and I try to use my time in a good way and try to not to delay it too much. I would like to talk about chiral superconductivity and enhanced quantized Hall responses in Moiré transition metal dichalcogenides. So let me just jump right into it. Here's my outline. I briefly will give you motivation on why I would like to discuss yet another Moiré system, despite the fact that we still have something to do with twisted bilayer graphene. So why I'm doing something else. And after that, I would like to discuss the band structure of these Moiré transition metal dichalcogenides to show you how to construct an effective, frustrated, extended superlattice Hubbard model on the triangular lattice, actually. So this will be my contribution to this particular session. That's where the frustration comes in, basically. And that model I would like to discuss somehow attack with the functional renormalization group approach. And I will show you that there's actually some very nice unconventional form of superconductivity, not maybe the usual one that you would have expected, which is chiral D-wave superconductivity, but some higher order superconductivity, and we'll discuss the quantized Hall responses that follow from that particular type of superconductivity. This work has been done together with Laura Claassen, who is also in the audience. Of course, you know her because she's part of this institute here. Then my PhD student from University of Cologne, Cognized, and Dante Kennis from Aachen. So let's get started. Here's my motivation to look into the slightly different Moiré system than twisted bilayer graphene. So to motivate that, let me just mention that for different reasons, we've been quite enthusiastic in the last 10 to 15 years about single layer graphene in the first place. But one of the reasons that we would have enjoyed graphene even more did not show up. That is strongly correlated behavior. And that was not for the lack of trying. So there are a lot of interesting theoretical suggestions of what could happen when the interactions, for example, would just be strong enough, and which type of phase transitions there could be, and which critical behavior. But so far in experiments, there are no signs of strongly correlated behavior, at least none that I know of. But the situation changes considerably when you just add a second layer on top, which is only weakly coupled in sense. But you can do that. You can look at bilayer graphene and give it a small twist angle. And what happens then? Of course, by now we all know that a strongly correlated phase diagram emerges. And so this was one of the first plots that basically started this whole wave of interest that is connected to that field of research now, where people observe that in contrast to what you would be expecting from a single particle picture, you see correlated insulating behavior and two domes of superconducting behavior next to it. And that is the starting point, and one of the reasons why twisted bilayer graphene was praised as a new platform for strongly correlated behavior. And I think to some extent it really held up to that promise, because we discovered many more different types of strongly correlated states, including quantized anomalous Hall states, but also orbital magnetism, of course, superconducting states, and many more. But there's another thing that is worth mentioning at that point, that is that twisted bilayer graphene is actually not so simple. If you look at it, also from a theoretical point of view, at least there are at least 4 spin-degenerate nearly flat bands in the middle of the spectrum, which are actually the active bands in that system. Then you have to go to specific magic angles where everything of that shows up, and then there's an issue of topological obstruction, which tells you that if you want to keep all the symmetries and topological properties of the flat bands in the middle, you have to take into account a large number of bands in your modeling, and that is of course a sort of a nightmare for strongly correlated methods, for quantum many-body methods. So then what can we do to make things simpler? We can think about what other options we have instead of just using graphene as a platform to model these Moiré materials. And in fact, we do have a whole class of 2-dimensional materials. ranging from semi-metallic systems over insulating systems over to semiconducting systems. And I would like to focus on the two ones here, the transition metal dichalcogenides. Here in this example, it's molybdenum disulfide and tungsten diselenide. As you can tell, I practiced these names quite a lot before. And this is what we do. So we will look at a system of these two semi-metallic, semi-conducting materials. And so let me first remind you of what happens when you put two of these two-dimensional materials on top of each other. They all have a hexagonal lattice structure, and if you put two identical layers on top of each other and rotate them, for example, by an angle of 5 degrees, you see that there's a nice Moiré pattern showing up with these AA stacking regions and in between AB and BA stacking regions. And but basically the same effect can appear when you do not twist, but you just choose different layers with slightly mismatched lattice constants. So this is an example where there is no twist angle, but the lattice constant of the top or bottom layer, you can tell by the picture, is just a tiny bit larger than the one of the other layer, and you still get a nice Moiré pattern with AA and AB stackings and all of that. So essentially the same effect, also an interference pattern. Now, in order to think about what will happen for the electrons near the Fermi surface, when you have such a pattern, we can recall that the ions of the lattice sites, they generate a crystal potential for the electrons, of course. And the crystal potential of the bilayer system will, of course, be a superposition of both layers. And that means that the electrons in this bilayer system, of course, they move in not only in the microscopic atomic lattice, but also they are influenced by the hexagonal Moiré superlattice, which will be important once we think about how we can model this in a quite efficient way. We don't want to go into atomic modeling. So there's a fairly simple relation of how the Moiré lattice constant, which, for example, connects the AA stacked regions, can be calculated. So it's basically the microscopic atomic lattice constant divided by the square root of the twist angle squared plus the lattice constant mismatch squared. And if we exactly play that game for the two materials that I have mentioned before, which have these two different lattice constants, we realize that there will be an effective Moiré lattice constant, which has the size of 8.5 nanometers, which is like more than 20 times, of course, the microscopic lattice constant. Okay, so now before we can really discuss what happens as a result of this Moiré potential or this Moiré interference pattern, we first have to understand what the band structure of a single layer of one of the transition metal dichalcogenides is. And for reasons that will become clear at the end of this slide, I will first focus on the case of monolayer twisted of monolayer tungsten diselenide, which has its band extrema at the two inequivalent corners of the Brillouin zone at the K and the K prime point, and there it looks like this. So basically, it's a spin split bands due to the spin orbit coupling in the tungsten diselenide, and we have a Fermi level which is really close to the valence band maxima of this particular spin configuration, where the one valley is the one on the left side and the other valley is the one on the right hand side. And there's a spin valley locking going on due to the spin orbit coupling here. And we can focus on this particular, even if we are considering the Moiré system consisting of these two different transition metal dichalcogenides, we can focus on this one, because when you look at this thing a little bit closer from the sub initio calculations, you realize that the Fermi surface is really close to this valence band maximum of the tungsten diselenide, but it lies really deeply within the gap of the other material, which is shown in the green in the semiconducting gap molybdenum disulfide. So basically, when we look at the active electrons close to the Fermi level, we can basically ignore the effect of the molybdenum, but we'll have to take into account, because what it really does, it makes this Moiré pattern. So it introduces a new periodicity into the system, which we have to take into account. So we will focus on these tungsten diselenide valence states, which lie inside the molybdenum disulfide gaps. And now, in order to get on with the modeling for the Moiré system, we'll have to consider the periodic, the additional periodic modulation due to the Moiré interference pattern, which is expressed in terms of this Moiré potential. And I've plotted this here. So basically, as a function of the x and y coordinates measured in units of the Moiré lattice constant. And this can obviously, due to its periodicity, approximated by Fourier series, which I just can cut once I have included all nearest neighbors. And due to symmetry reasons, the whole Moiré potential is basically fixed by two parameters, which is this prefactor here and the phase factor. And this can be measured with scanning tunneling, with a scanning tunneling microscope. And there's a parameter fit from previous measurements, which just determine these two parameters. There's a certain level of tuning that you can play around by proximity with additional substrates and everything, but this is one example of how this can be realized. All right, so let's put together all the ingredients. We have said that we can make an effective mass approximation for the maximum of the valence bands of the tungsten diselenide. So we can approximate this by this standard kinetic term. Then we'll add the Moiré potential, and eventually what we can do is we can basically deduce the dispersion of the Moiré-Bloch Hamiltonian then in a plane wave representation by just diagonalizing this these matrix elements within a reasonably large lattice. So this basically falls back to the nearly free electron approximation that we all know from our introduction to solid state theory. And if we do this, yeah, this you can basically calculate straightforwardly from diagonalization of the Moiré-Bloch Hamiltonian. You get a bunch of bands. Of course, if it would just look like this, you would not see a lot. So let me zoom in a little bit. What you basically see that at the top of the valence band, you obtain an isolated single band that is separated by a band gap from all the other bands. And it features a very narrow bandwidth, which in that particular case is 20 millielectron volt. Of course, because of the tuning freedom we have, we can still play around with the width of this band, and also by considering a couple of other modifications, for example, in terms of changing the Moiré potential. So that's already very nice. So we have a fairly flat band, which is isolated from all the others. And now, the story goes on like this. Now we can wonder whether we can put this single isolated band into a little bit of a different modeling, because we don't want to consider all the other bands once where we're going for a quantum many-body approach to the correlated physics of this Moiré system. So what we can do is we can basically use an effective tight binding description of this band, and since basically the effective tight binding model that we have to write down now lives on the Moiré lattice, because this is exactly the lattice or the real space lattice size that gives us the right size of the Moiré Briand zone, of course. So what we can basically do is we can write down a standard tight binding model, and then introduce a nearest neighbor, second nearest neighbor, and third nearest neighbor interaction, and fit these parameters as well as we can. And it turns out this works quite well if we choose this set of parameters. And let me also just mention that when we have an option to increase the Moiré lattice constant, the general tendency of these parameters is that they decrease exponentially even. So we can make the band flatter and flatter if we see any need for that. Okay, flat bands are good if we want to force the system to become strongly correlated, but at the same time we also have to worry about what the interactions do, because if they are suppressed in the same way, then we want nothing. So we can briefly look at what happens when we consider the localized Wannier functions that would correspond to these flat bands. And just a very rough, basically a qualitative argument that we can start here is that we can go to the minima of the Moiré potential and just put a localized Wannier function in there and look at how large this is. And the size of this Wannier function is basically given by the size of the ground state of the harmonic oscillator that would just sit in that well. We can just read that off. So basically, the size of the Wannier orbital would be proportional to the square root of the size of the Moiré lattice constant, and that gives us a very neat way to calculate the on-site matrix element for the Coulomb interaction, which then scales with e squared over 1 over the Wannier constant. And since this has a particular scaling with the Moiré lattice constant, we know that once we increase the Moiré lattice constant, the on-site repulsion only decreases very slowly, in contrast to the decrease that is exponential in the hopping parameters. So that means effectively what we have here is, by tuning the Moiré lattice constant, we have a quick increase of the ratio of the interaction energy as compared to the kinetic energy. And that, of course, supports the formation of strongly correlated states. So let me just summarize very briefly how I constructed this model, and then I really go to the strongly correlated part. So what we do have here is an extended Hubbard model on the triangular lattice with T1, T2, T3 nearest neighbor hoppings. And then we will also get, if we play this game further, which I indicated before, we will also get interaction parameters. Let's first focus on this tight binding part. It's defined on triangular superlattice, so it features geometric frustration. If you look at the Fermi levels here, we get Fermi surface nesting even at some Hove singularity. It's actually at 3/4 hole doping. So we have to hole dope the system because we're located with the charge neutral Fermi surface at the top of the valence band. But what you can actually do, because the band is so narrow, you can access the full range of band fillings by electrical gating. So just as you would have assumed for twisted bilayer graphene. Then there is a tunable strength and range of the electron-electron interactions. It's tunable by vicinity to a substrate, for example, or modification also of the Moiré potential. But what is important here is that when you really calculate those Coulomb matrix elements, you will find that there are sizable non-local terms, and this will be important once we're discussing the correlated states too. So keep that in mind, and I will give you concrete numbers once we are discussing what we're actually doing in terms of many-body methods. So what you can expect is that there's a complex interplay between the electronic interactions and geometric frustration. And we already know, and I think a couple of people in the audience are around that have found this, or at least some version of this model quite interesting in terms of strongly correlated phases, because there are mod insulator transitions, putative spin liquid states, there is exotic magnetism. For example, at half filling, there are very advanced, sophisticated many-body methods around. And yeah, I think some of the people in the audience have contributed to that question. What I would like to do, I would like to focus on the Van Hove scenario on the triangular lattice here. So where density of states shows a log divergence, and we have this nested Fermi surface as indicated here. And there are already also on that topic, there are a lot of previous studies which already established that there's some competing order scenario going on between a spin density wave with this scattering vector M1, M2, or M3. So the other competing tendency is the one for unconventional superconductivity, and there are also a couple of suggestions on the market for the leading unconventional superconductivity. So whether it's D wave, I wave, or F wave, and let me just mention here. So far in the study of this triangular lattice Van Hove scenario, the focus has not exclusively but strongly been on the case of the on-site situation or on effective models, like in terms of a Parquet RG. And what we would like to do here instead is we would like to take this model for the Moiré tungsten diselenide for the Moiré transition metal dichalcogenides seriously by really looking at the effective microscopic Hubbard model that we have formulated here, which is supposed to accurately describe the Moiré bands and the interactions. Some uncertainties, of course, but where we also take into account interactions up to the third nearest neighbor interaction. And we would like to explore what happens as an effect on the Van Hove scenario and superconducting pairing. So what I would like to do in that context is I would like to employ the electron functional RG. I will not go into technical details, and we are also not doing something unconventional here. So basically, we're just using this as sort of a discovery tool for ordering tendencies by starting with this microscopic model and then following the two-particle interaction vertex in its RG. Yes, I have the time in. Right, and look at the RG evolution of this two-particle interaction. So why do we think that's a good idea? It's a good idea because we can take into account the full band structure, the non-local interactions from the microscopic modeling, and we take into account the competition between all these different interactions channels. So roughly like the particle-hole channel instabilities and the particle-particle channel instabilities. And this is basically just for the people who are already familiar with the RG. So this is basically full disclosure. It's the standard level 2 truncation, which sums up the Cooper, Pierce, screening, and vertex correction channels. We neglect 6-point vertex and higher, neglect self-energies, neglect frequency dependence. So everybody who thinks they can do better are invited to do that, but maybe you need some more motivation. So let me show just what we find for this particular model. Benefits of this approach are that it treats all fermionic fluctuation channels on equal footing, and it corresponds to infinite order resummation of all fermionic one-loop diagrams. This is an even more technical slide, so maybe in view of the time running out on me, I will just skip this and just say that we do a channel decomposition into the pairing and into a C and a D channel. And we we have a high resolution of the momentum dependence of the vertex here, where we basically have this transfer momenta, which are marked here with QP, QC, and QD in this Briand zone mesh. And then we expand the remaining momentum dependence in terms of form factors, where we go up to a sort of a fourth shell of form factors, so reasonably high, I would say, which turns out to be not unimportant for the triangular lattice. So let me just show you the result here. These are my microscopic parameters from the model. These we discussed already in depth, and the interaction parameters are the following. So I take a U over D equals 4 that somehow sets the units or the level of interaction here. I fix these second nearest neighbor, third nearest neighbor interactions to fixed values, and I play around with the V1 just to explore its effect on the whole phase diagram. So basically, I have an interaction profile that I can modify within this within a certain range. So I can make it more long-ranged or shorter ranged. And then I explore the whole phase diagram in terms of the chemical potential, which determines my filling here. And close to the Van Hove singularity, where the nesting is almost perfect, we see that there's a valley density wave appearing. It's basically a standard spin density wave that you would have expected, but because the valleys are replace the spin degree of freedom, we call it a valley density wave. And then you have two superconducting domes here adjacent to the valley density wave, which I did not characterize so far. So that's the next step that we'll have to do. From our pairing vertex, which we have included in the channel decomposition of the two-particle interaction, we can write down a superconducting gap equation and solve that, and we can basically construct a superconducting gap. And what we do find is that this superconducting gap ends up to be in one of the two-dimensional irreducible representations of the C6V symmetry group, which is relevant to the triangular lattice. So just let me remind you how the form factors for this actually look like from the A1 to the E2, and you will see that in the first column, these are all the nearest neighbor lattice harmonics, and in the second one, except for that one, there are the second nearest neighbor harmonics. So if you compare these pictures, you will find that these two gap functions end up to be in that second nearest neighbor harmonic of the E2 representation. That you can also just find out by counting the zero crossings along the Fermi surface. So there's a reasonably well fit with these second nearest neighbor lattice harmonics, which are, when you count the zero crossings, which would fall into a G-wave superconducting state. They do have the same symmetries, obviously, as the first nearest neighbors from the E2. So you would have to ask why the system would prefer that second nearest neighbor, and the reason is clear. It's because it has to overcome the longer range Coulomb tail here, and it seems that this is the best state that the system wants to realize, because the pairing is pushed outward. And now, of course, one question remains before I come to my conclusion, and that question is: can we, because the symmetries are actually the same, can we actually distinguish these two different superconducting states, so the D wave and the G wave, which are both in the same irrep? To that end, you can construct Landau theory, which you can basically, where you take into account both form factors or both gap functions, and you will find, so this is really rushing through, you will find that the best state that you can construct out of that is the one with the same amplitude but a complex unit in front of it. So basically classified as a G plus IG superconducting state. And if you just look at the phase winding of this superconducting state, you will find that it winds 4 times around the Fermi surface. So to quantify this a little bit further, what you basically can do is you can use this G plus IG superconducting gap to define a pseudospin vector, and from that construct a topological winding number, which gives you this topologically invariant. And if you compare now the G plus IG state with the D plus ID state, you will find that this topological invariant is plus or minus 4 instead of being plus or minus 2. So despite having the same symmetries under this C6V point group, we have to deal with two topological different states. And that reflects in the number of edge modes, which are given by this topological winding number. And if you look how this number of edge modes goes into the spin Hall or the thermal Hall conductance, you will find this is a multiplicative factor. So that means if we really have this G plus IG superconducting state, then we get enhanced quantized Hall responses as compared to at least the more conventional, unconventional D-wave chiral superconductivity. So that brings me to the end of the talk. I did not really exceed it too much over the 12 o'clock lunchtime. Let me just briefly summarize. Basically, what we have found is that we can simulate an extended Hubbard model on the triangular lattice with Moiré transition metal dichalcogenides. We find that non-local Coulomb interactions, this has been found before, are likely to be relevant in these systems, and the Van Hove scenario is accessible. With the FRG that I presented you, we have resolved the competing orders and found that this chiral G plus IG wave superconductivity is likely and appears in extended parameter region. So this was not just a single spot in the phase diagram, but basically the whole vicinity of the Van Hove singularity. Find that it has a topological Chern number of 4 and features enhanced quantized Hall responses. And if you want to read more about that, please consult these references or just approach me and we can discuss this. Thank you.